By now, it should be evident that much of the process of cognitive development depends on the capacity to remember. In the development of language, memory is involved in infants associating certain sounds they hear with images they see and connecting these associations to the prefrontal cortex using the arcuate fasciculus. It is also involved in learning to connect the visual images of the words on the pages of a book with the meaning and implications of those words. While the memory involved in developing language and the ability to read is important, memory comes in more than one shape and size. Multiple different parts of the brain are involved in forming these memories. In this lecture, we will look at many of these forms, classifying them into two general categories: long-term memory and short-term memory. I will illustrate these two types of memory first by sharing with you from memory one of my favorite poems. Two roads diverged in a yellow wood, and sorry I could not travel both and be one traveler. Long I stood and looked down one as far as I could to where it bent in the undergrowth. Then took the other as just as fair and having perhaps the better claim, because it was grassy and wanted wear, though as for that, the passing there had worn them really about the same, and both that morning equally lay in leaves no step had trodden black. Oh, I left the first for another day, yet knowing how way leads on to way, I doubted if I should ever come back. I will be saying this with a sigh somewhere, ages and ages hence. Two roads diverged in a wood, and I took the one less traveled by, and that has made all the difference. This poem is titled The Road Not Taken and was written by Robert Frost. Many students study this poem in high school. I often share the poem with students at Stanford who come to my office to discuss choices they are confronting: career choices, choices of academic programs, personal choices. I will usually print out a copy of the poem and give it to the student, show them this image of a yellow wood, and then recite the poem from memory as they read along. We then discuss whether there really was a, quote, road less traveled, unquote, since Frost tells us that the passing there had worn them really about the same. Also, for anyone who has seen an autumn leaf fall in Vermont, you will appreciate that it would be nearly impossible to determine which road was less traveled when both were covered in leaves, no step had trodden black. However, instead of meeting with students, when I walk into a grocery store to do some shopping, if there are more than 3 things I need to buy, I have learned to make a written list. 9 times out of 10, when I go to the store to buy 4 or more things, I will forget one of them if I don't have a list. The difference in these situations is that I had decided what items I needed from the grocery store only a few moments before I got to the store, having stored those items for the moment in my short-term memory. By contrast, it took reading the Frost poem many times and gradually learning more lines from the poem until I could recite the entire poem from memory. Once I had done this, the poem was stored in the part of my memory that would keep it there for the long term, ready for me to access when I needed it. In a paper published in 1996, Squire and Zola differentiated between what they referred to as declarative memory and non-declarative memory. They defined declarative memory as the capacity for conscious recollection of facts and events. They contrasted this to non-declarative memory, which they described as a heterogeneous collection of non-conscious learning capacities that are expressed through performance. By their definition, I'm attempting to use declarative memory when I go to the grocery store without a list, and non-declarative memory when I recite poems from memory for my students. They distinguish between the two forms of memory by suggesting that, quote, declarative memory supports conscious recollections, whereas non-declarative memory does not afford awareness of any memory content, unquote. If you will recall my son's performance of Copland's piano piece titled The Cat and the Mouse, it was part of an earlier presentation, you will appreciate that he was not consciously aware of what his hands were going to do. Rather, he was able to let go of conscious control and let his hands perform the piece, relying on non-declarative memory. Similarly, when I'm able to recite from memory a Robert Frost poem, I must first let go of conscious control and let the poem speak for itself. In his book, The Learning Brain, Memory and Brain Development in Children, Swedish neuroscientist Torkel Klingberg uses different terminology to refer to these fundamental divisions of memory. He refers to them as long-term memory and working memory. As described by Klingberg, the long-term memory is the memory system that stores learned facts, rules, names, and experiences. It's the memory that stores what we traditionally associate with learning at school. Working memory, on the other hand, keeps information up front just when we need it and holds relevant items in our head when we're solving a problem. The characteristics of working memory include a relatively short time period during which it works, the fact that information stored in working memory is only there temporarily. As soon as it is no longer relevant, it will be let go. As we will describe below, we use working memory when we want to manipulate information, such as performing mathematical calculations in our head. Finally, part of working memory is used to focus our attention on the mental task or tasks immediately at hand. In this sense, one of the principal tasks of working memory is what is often referred to as maintaining executive control over our thought processes. In their online article on working memory, UK professors Alan Badley and Graham Hitch of the University of York suggest that working memory has two central components: short-term memory, which refers to information storage without manipulation, and executive control, which describes the capacity to focus attention, to divide attention between two or more tasks, and to control access to long-term memory. As shown in this illustration taken from an online teaching resource provided by Landmark College in Vermont, we see that the executive control function is largely a responsibility of the frontal lobe through its many axonal connections to other cortical areas. As one might imagine, our short-term memory takes a wide range of stimuli from various sensory inputs and components of the external environment. While the short-term memory can temporarily store these inputs, it is necessary to select among them the ones that will focus our conscious attention. For example, while attempting to do a difficult math problem, we need to ignore many other visual or auditory stimuli around us so we can do the mathematical manipulation. Similarly, planning and organizing how we will spend our time and focus our attention is key to many cognitive tasks, not the least of which is succeeding in school. In addition, while we may be prone to many impulses from various sources within our conscious and unconscious awareness, our executive control function enables us to control many of these impulses so as to focus our attention on the task at hand and plan ahead as to how we will spend our time. Psychologist Daniel Kahneman also describes two aspects of memory. Rather than calling them long-term memory and working memory, he refers to them as System 1 memory and System 2 memory. System 1 memory, which is analogous to long-term memory, quote, operates automatically and quickly with little or no effort and no sense of voluntary control. Playing a complex piece by Copland or reciting from memory a poem by Robert Frost relies on our System 1 memory. By contrast, System 2 memory, as described by Kahneman, quote, allocates attention to the effortful mental activities that demand it, including complex computations, unquote. This aspect of memory is analogous to working memory or short-term memory. Kahneman refers to these two processes in another way that seems intuitively useful. As the title of his book suggests, he refers to System 1 as thinking fast and System 2 as thinking slow. He provides an instructive example of these two modes of memory. He asks us to find the answer to the following two mathematical expressions. What is 2 plus 2? What is 17 times 24? We all know that 2 plus 2 equals 4. We learned that sometime in our childhood, and it has stayed within our System 1 memory since then. We don't actually need to do a mathematical computation to answer this question. The entire phrase of 2 plus 2 equals 4 is stored within our brain cells, ready for us to call on when prompted. On the other hand, to calculate 17 times 24, I can close my eyes and try to go through the steps I learned in school. Let's see, 7 times 4 is 28. Put down the 8 and carry the 2. Or I could use a pencil and paper or a calculator to assist me. To do any of these, however, I must put other things out of my mind and focus on the short-term process of completing the appropriate steps in the appropriate sequence to find out that 17 times 24 equals 408. If, as Kahneman suggests, most of what we do involves our System 1 memory, how does information get transferred from System 2 to System 1? The key to this transference process is the hippocampus, which is part of the temporal lobe. As an association passes through our System 1 memory structures on a repeated basis, the hippocampus gradually transfers those associations to a different set of neurons. This new neuronal connection relies heavily on the prefrontal cortex to store them as long-term System 1 memories. In his 2011 book titled Incognito: The Secret Lives of the Brain, Eagleman describes this process as, quote, rewiring your own circuitry until it can accomplish the task with maximum efficiency. The task becomes burned into the machinery, unquote. As described on the website The Brain, provided by McGill University in Canada, quote, after a while, these various cortical regions activated during an event would become so strongly linked with one another that they would no longer need the hippocampus to act as their link. Thus, information that has been encoded in long-term memory for a lengthy period of time no longer requires the intervention of the hippocampus, unquote. Thus, the role of the hippocampus is to convert frequently occurring associations from working memory into long-term memory through the myelination of a specific network of axonal connections. Research by Kin and colleagues, published in 2014, addressed this question in a study of 28 children between the ages of 7 and 9, recruited from elementary schools in the San Francisco Bay Area. On 2 separate occasions, separated by about 14 months, each child was asked to perform 2 age-appropriate mathematical calculations. One of these was done by having the child explain to the researcher how she or he had solved the problem. The other was done while the child was undergoing an MRI scan of the brain. The questions the researchers were attempting to answer were, first, does the child's mathematical ability improve over this 14-month period? And second, is there evidence that over time the children rely less on the counting strategies typical of System 2 working memory and more on rapid recall of answers from System 1 long-term memory? The answer was yes to both questions. The children's mathematical ability increased over the study period. They also found that for the first test involving simple addition such as 4 plus 1, the children relied largely on the process of counting that uses working memory, shown here in blue. By the second examination after 14 months with slightly more complicated problems, for example, 5 plus 9, they relied less on counting and more on long-term memory, shown here in red, to solve the problem. The researchers then compared the results of the MRI scans at the 2 assessments. Consistent with the manner in which the children solved the problems verbally, while doing the problem in an MRI scanner, they used different parts of the brain to solve the problem. To solve the problem at the first assessment, the children used principally the part of the brain involved in working memory. In solving the problems at the second assessment, they instead used less working memory with greater activation of the hippocampus and its white matter connections involved in long-term memory. From this, the authors were able to conclude that in learning mathematics, quote, we observed a shift from the use of counting to memory-based strategies in children over a 1.2-year interval, and this was associated with an increased hippocampal engagement in problem solving. The increased hippocampal engagement is consistent with its known role in learning and memory for encoding and retrieval of facts and events. Thus, our longitudinal findings suggest that the recruitment of hippocampal-dependent memory processes is important in the development of children's memory-based problem-solving strategies. Unquote. The authors then also recruited and studied the mathematical ability of 20 adolescents between the ages of 14 and 17 and 20 young adults between the ages of 19 and 22. These older subjects were asked to solve more complex math problems. In doing so, the subjects relied heavily on long-term memory rather than the counting typical of short-term working memory. In solving the problems while undergoing an MRI scan, these older subjects showed activity of the white matter axonal connections involved in long-term System 1 memory without concurrent activation of the hippocampus. In these subjects, the work of the hippocampus in converting working memory to long-term memory was largely done. The adolescents and young adults had developed the myelinated axonal connections necessary to retrieve the memory required to solve the problem. From these results, the authors concluded that, at least in learning mathematics, quote, the hippocampus has a time-limited role in the early phase of knowledge acquisition. Our findings suggest the hippocampal system is critical to children's early learning of arithmetic facts, the retrieval of which is largely dependent upon long-term memory in adults. Through further schooling and experience with mathematics, fact retrieval becomes increasingly independent of the hippocampal memory system during adolescence and adulthood. Unquote. While the authors studied this process only in the development of mathematical ability, they suggested that the same processes may be involved in learning language and other academic abilities. This would suggest that when I first worked on learning Frost's poem about the road not taken, I used my hippocampus to convert the individual words and phrases in the poem to long-term memory based on the myelination of a series of axons. Now, when I recite the poem, it comes directly from those axons without further involvement of the hippocampus.